Predicting the product, substitution versus elimination. So in the beginning of the chapter we mentioned that substitution and elimination reactions compete with each other. And sometimes they compete more or less successfully, and so more than one product can be made. In order to predict products, you're going to want to determine the function of the reagent. Is the reagent going to act as a base, or is it going to act as a nucleophile? Analyze the substrate and determine the mechanism. And lastly, consider the regiochemical and stereochemical requirements of the reaction. So first, let's look at determining the function of the reagent. Strong nucleophiles are going to lead to substitution reactions. Strong bases are going to lead to elimination. Strong nucleophiles are going to have high electron density and they're going to be polarizable. This is a kinetic effect. Strong bases are going to be unstabilized, and that's a thermodynamic or equilibrium effect. Good nucleophiles are not always good bases. You might think that they would overlap, but they don't. Bromine is a great nucleophile. But it's a weak base because it's very stable. It's a large atom and it's able to stabilize that charge, and so it's a weak base. I didn't put base in here, but there we go. Weak base because stable. Sodium anhydride is a poor nucleophile because it's too small to polarize. It's a very strong base because hydrogen is such a weak acid. So these are the general categories of reagents. We find that sodium anhydride, DBN, and DBU are strong bases but weak nucleophiles. So we would expect a strong base to favor elimination. Then we have all of these compounds that have charged oxygen. So all of these have a charged oxygen. And we find that they can either function as a base or a nucleophile. They are not large enough to be stable. That makes them a good base. They have that charge, and that makes them a good nucleophile. The next section of category is weak base and strong nucleophile. And here we find large atoms that are able to stabilize the charge, making them a weak base, but having a charge gives them makes them a strong nucleophile. And so we would expect these to be involved in substitution. And then we have the compounds that are neither. They're not a good base, they're a weak base, and they're a weak nucleophile. So let's look at the substrate. If we have a strong base and a weak nucleophile, like I said, we expect these to be an elimination, and they are. It doesn't matter what the substrate is, they will engage in elimination. Let's skip the strong base, strong nucleophile for a minute and go to weak base, strong nucleophile. These, I said, would be involved in substitution. And so we expect to see substitution. We see an SN2 reaction if it's primary or secondary. If it's tertiary, we can't have an SN2 because it's too sterically inhibited. We get SN1. Okay? So let's go back then and look at the strong base and strong nucleophile. These can go either way. They can be involved in elimination or substitution, and it depends on the substrate. A primary substrate will get SN2 substitution for our major product and an E2 for our minor product. If we go to a secondary structure, then E2 predominates and SN2 is the minor product. If we go to a tertiary substrate, remember we said we can't have an SN2 reaction on a tertiary substrate, and so it's all E2. If we have a weak base and a weak nucleophile, this last one, we'll get an SN1 and E1 reaction. Here we're going to make a carbocation, and then it gets attacked. So let's look at this example. Here we've got sodium hydroxide is our substrate, and if we look up, sodium hydroxide is here. It's a strong base and a strong nucleophile. I abbreviate that: strong base, strong nucleophile. This is a primary substrate, and so we expect to see elimination as our minor and SN2 as our major. If we have a secondary substrate, the same reagent, we expect to have the elimination as our major and the substitution as our minor. If we go to a tertiary substrate, we only get the E2. Let's do some, one more thing before we go. If we use a sterically hindered base, this is the tert buoxide, that looks like, it'll look like that, and it's very sterically inhibited. You'll favor elimination, even in a primary. So our major will be an elimination. Okay, so let's identify the major and minor products. So for each one of these, the first thing I'll do is look at the reagent. We've got a chloride, so this is a weak base and a strong nucleophile. Our substrate here is secondary, and so I'm going to expect to have an SN2 reaction. So I will get something that looks like that. I'll have an inversion of form. All right, so here we've got sodium hydroxide. This is a strong base. It's also a strong nucleophile, but we have a tertiary substrate, so we'll only have E2. We look at what can be formed. We've got, let me get some colors in here. Do green. We've got a hydrogen here, and we've got a hydrogen here. There's also a hydrogen here, but it's the same as the green one, so we will get, let's see, which color? I've got the orange color, so we'll do this one first. If we take the orange one, if we take the green one, we'll get and those are our two choices. There is no cis and trans here because these are the two methyl groups off here are the same. Okay, if we have this compound and we use this reagent, we have a strong base and a strong nucleophile. We've got a charged oxygen here. It's sterically hindered. And our reagent is tertiary. That will end in an E2 reaction. So we look and let's get some colors in here. We've got a hydrogen here we could take, and that will give us that compound, or we could take the hydrogen from here, and that would give us so DBN, we were told, you can look up the structure in your book if you're interested in it. It is kind of an interesting structure. It's a strong base and a weak nucleophile. So we will expect an elimination reaction. Reagent here is also tertiary, so we'll get an E2 reaction. See, where are we going to pull our hydrogens from? There are no hydrogens here. So we have a hydrogen here, and it looks like that's the only one we've got, so only one thing will be made. Let's look at E. We have a strong base and a strong nucleophile. It's sterically hindered. So we'll expect an elimination reaction because it's sterically hindered to be our major, and it will be an E2, and we'll get 1, 2, 3, 4. Make sure we get the right number of carbons. That will be our major. And our minor will be this is the E2 and this is the SN2. If we use instead a sulfur compound, we'll have a weak base and a strong nucleophile, and we'll expect on a primary substrate, and we'll expect it to be an SN2. Here we have sodium hydroxide, strong base, strong nucleophile. Let's see, we've got a primary substrate, so we'll expect the SN2 to be major, and that would look something like this. We'd also expect to get some elimination, and our elimination product would look like that. It's E2. H is our last one here. So we've got a strong base and a strong nucleophile. We've got a primary substrate. So we'll expect to have an SN2 reaction to be our major component, our major product. and we'll also expect to get some E2